Alright, welcome back. Let's take a look at number 3. They're giving you this crazy equation that measures the sunlight, the number of minutes of sunlight every day, starting in 1996, it looks like. So, anyway, it's a goofy looking equation, and I don't ever expect anybody to actually see an equation like this again, but nonetheless, it is a calculator section. So the first thing I did was decided to put this into the calculator, and of course when you first look at the graph, if you're in a standard window, you don't see it. So I'm going to do a zoom fit, so it's either 9 or 0 if you're using an 84. And when you do that, you only see a part of the graph here. So what I would like to do is I'd like to talk about what this equation's what they're asking us for. And here they really want us to look at every year this thing is going to just repeat itself over and over, because it's the sine. It's just a function that keeps repeating itself. So let's just first of all start off the discussion with just what does sine look like. So sine starts off at the origin and it just keeps going up and down. So it's periodic. It doesn't matter, all this stuff just adjusts the basic sine function. Of course, since we're looking at a whole year, if we want to see the whole year, what will we do? Well, since D is days, we would need to get 365, but in this problem, they're asking us about 1996, so all you do is, after you do your zoom fit, don't change anything except for the X values, because X's are days, right? So let's see what happens if I type in 366 here. If I can do that, 366. And let's see if this shows us anything. Well, now we don't see much of the graph in here. So let's try doing a zoom fit again. Sometimes it just takes a little playing around with the calculator to figure out how this thing is going to work. Okay, when I did another zoom fit, after I adjusted the X window, you can see this nice curve right here. Alright, I'll copy it on there so we can talk about it in a second, but let's trace it. Let's trace this. So what is the graph actually telling us? At X equals 1 day, there's 567 minutes. And if we trace to the end, which would be December 31st in this problem, because of the leap year, you can see that there's about the same number of daylight minutes in January the 1st and December 31st. So you expect that the most number of daylights is going to be somewhere, during the summertime. So sometimes it helps just to talk about this. So this is in the summertime, and this is in the winter time here. So this is day 1, day 366, and then after this next year, it just does the same thing over and over, right? Alright, well, let's take a look at this, and let's just look and see what they're asking us. On part A, they're saying which day has the most minutes of daylight. Well, you can see that this reaches a local maximum right here. Actually, this is a relative max, which turns out to be the absolute max, because this function just repeats itself. So how do you talk about relative maximums? Well, you're going to have to take the first derivative. So don't get too confused. If this was just the derivative y equals 10 sine of 2x, how would you take the derivative of that? 10 is a constant, so it comes out. The derivative of sine is cosine of 2x. And this is a chain rule because this is not, the angle just isn't x by itself. So what's the derivative of 2x? Just 2. So the derivative of our little example is 20 cosine of 2x. So certainly you can see that if you were to distribute this into here, the d, which is our variable, is associated with 2 pi divided by 366. So in our problem, L prime of d, instead of having 2 in there, we have 2 pi over 366. So we multiplied by 2 because that was the coefficient in front of x. Now our coefficient is just this 2 pi over 366. And of course, what happens to 731? It goes to 0. So certainly, you could set the derivative and see where it's equal to 0, and you'll find out it's right there. Another way to do this, since this is the calculator, you could mention the derivative, and on the calculator, since we already have it graphed right here, you could do what? You could do a maximum, number 4. And the left boundary should be on the left side, not on the right side, so that 2 is way down here. You could use the arrow keys until you get over the hump. You can see my spider's moving up. I'm at 110 days, 126 days, and it looks like it's still increasing. Now it's going down again. Let's get it all the way on the other side so you can see it. So right here, clearly we're on the other side of the relative max. Hit enter again, and it looks like the maximum occurs at 171 and a half days. All right. Well, let's move on to part B and just talk about what it's asking us about. What is the average mean number of minutes of daylight in 1996? And they want us to justify it with calculus. So you're going to have to use the formula for average value of a function, which is the integral from a to b of whatever my function is, right? And then outside of that, don't forget that you multiply it by 1 over the top minus the bottom value. So in our case here, they're asking us about 1996. So what are we going to have? We're going to have day 0 to 366 over 366 minus 0. And they're asking about the mean number of daylight, right? So they're asking us about the daylight, and that was the original equation, not the derivative. So remember, you don't need to rewrite this entire formula. You just need to write down what they defined it as. So that would be L in terms of D, and I guess dd. Instead of dx, we're going to use dd because that's the variable. So since you already put this in the calculator, of course you can use your calculator to justify your answer. But don't forget your units. Don't forget your units, which would be what? It's going to be in minutes, right? Okay. um, Part C, which is the last part. What is the total number of daylights in 1996? Well, all we have to do is just find the area under this curve. Not the average area, but the entire area. So we're just going to use this portion of the formula. Let me just rewrite it. So in part C, we would go from 0 to 366 of LD dd. Okay. It's not too bad of a problem once you understand what it's asking you for. And if really being able to manipulate your calculator, it will give you a lot of shortcuts, okay? So first thing we had to do was be able to see this graph in its entirety. And we did that by using our zoom fit feature. Not only once, but first time we did it, we went in and adjusted the window, and we changed our x value because x values were the same thing as the number of days. And since we wanted to look for an entire year, we used 366 because in our problem, 1996 was a leap year. They told us that, and we had to adjust out. And then we did another zoom fit so that we could see the entire picture. Okay, so if you don't have a calculator handy, and you're at a computer, you most definitely want to download the Flash debugger. So if you go to Google and type in TI-83 Flash debugger, you should be able to download a free version of that, and you'll be able to use the calculator on the screen just like I do in class. Okay, hopefully this problem is not too tricky for you, and just keep in mind that being able to get a few points here and a few points there, not worrying about being perfect on this thing because time is a factor. So anyway, I'll pause this now and we'll start off with the next question in a minute.